All right, good morning.
Good morning.
So we are in the second part of the course now, which is dealing with quantum chemistry and eventually into chemical bonding. So we're going to start with chapter 6, and then we're going to go ahead to 8 and 9 to do chemical bonding. And if there's time at the end, which there might be, the pacing is pretty good right now. I might come back and do a little bit of 7. And even, well, maybe a little bit of 11 as well. We'll see how that goes. Very good. All right, so let's talk about chapter 6. What we've done thus far is we've talked about the macroscopic description of matter. So when we talk about mass measurements, which was chapter 3, and then the chemical reactions, which was chapter 4, and then the thermochemistry, which was chapter 5, and then the gases finally, right? Chapter 10. This is all what we call macroscopic. We'll call it the study of chemistry. So in a sense, it's old school. It's old school physics, old school chemistry. It's the science that was developed, for the most part, prior to our understanding or our interest in the structure at the atomic or the molecular level, the microscopic level. So what we're going to look at in chapter 6, well, let me do it here. So quantum, I'll just call it quantum for short, which is chapter 6. Bonding in chapter 8, bonding 2 in chapter 9. What we're going to be interested in is the microscopic study of chemistry. Okay, so we've kind of gone over the macroscopic. There's a little bit in chapter 11 there. You go back to the macroscopic, but for the most part, we're going to study the microscopic. Now, the reason that it's useful to kind of separate these two into two categories, one is kind of historical, which is those first 4 chapters, that material was discovered and studied, going back to the age of antiquity, going back a long ways with alchemy and things like that. But this, chapter 6, 8, and 9, this is all pretty modern historically when you think about, humans studying the universe, maybe for the last 150,000 years or so. So 150,000 years is, pretty short period of time geologically. The universe is almost 14 billion years old, and the Earth is almost 4.5 billion years old, and life is 3.5 billion years old. 150,000 isn't very long. But when we come into this idea of the microscopic study of chemistry, what we're going to talk about over the rest of the course is really only 120 years old, 130 years old at most, right? So that's a pretty small fraction. That's about 0.1% of the time that humans have been studying the universe that this information has been elucidated. And so let's take a look beginning at chapter 6. What we're going to do is we're going to start by talking about light, the light that we see with our eyes, the light that we feel is in the form of heat when it strikes our skin. We're going to begin by studying light, and then that's going to lead us into thinking about waves. And then as we think about waves, that's going to lead us into the electron. And since atoms are composed of nuclei with electrons, that's going to lead us into the structure of the atom. And then once we figure out what the electrons are doing, that'll allow us to start thinking about chemical bonding. So let's begin by talking about light. So light is something we're all familiar with, right? We know we have different colors, right? There's violet is a color, blue is a color, green is a color, yellow, orange. These are all some of the colors out there. And then we have different hues, you know, there's different, like pink is a shade of red, for example. There's typically in the sciences, we kind of squeeze in here another color, which is called indigo, which I have to say, even to this day, I'm not a real expert on the difference between violet and indigo. I mean, I love colors, but I'm not a real expert on them. But in any case, it's often useful to throw a seventh color in there. And the reason for that is that it leads us to an what do you call it? I don't know how you pronounce it, mnemonic, mnemonic, a mnemonic, which allows us to remember this order. And it's Roy G. Biv. I'm kind of going backwards, I'm reading upwards. So Roy G. Biv meaning a name. So Roy, which would be the first name, G would be the middle initial, and then Biv would be the last name. And that just sort of allows you to like memorize the order of these colors. And the order actually ends up being important. We'll talk about the order later. So what do we know about light? Well, we know we like it, right? We don't like it at night when we're trying to sleep. We do like it when we are trying to be awake. Films, you know, think about all the technology that goes into light now, right? Like people want to have, you know, these really vibrant television screens and phone screens, right? So much of the cost of a phone is actually the screen, right? If you ever get one replaced, you recognize that. You know, vibrant colors. And part of that has to do with just the fact that humans are evolved to have, you know, really impressive vision, right? We can see different colors, and we can see really even sometimes very subtle differences, and they really excite, you know, parts of our brain. So we really like light. And, you know, light also keeps us warm, right? So, you know, you think about it this way, like when light strikes your clothing, and, you know, I'm wearing like a black hoodie right now, so that light hits it, what happens? It gets warm, right? And it feels good, right? Or sometimes it feels good. It could get hot and you take it off, right? But that right there, that tells us right there that light has energy, right? Somehow that light is being converted into heat, and heat is a transfer of energy, right? So there's energy in light as well, okay? We call it radiative energy. So we'll talk about the energy aspect of light as well. But what we want to do is we want to talk a little bit just about what we kind of, you know, have historically thought about light. Light is has been understood to be a wave. And a wave is a way that nature transfers energy, right? So if you think about it, as we speak, there are waves, some vibrations, compressions, and expansions of the air comes out of our throat, out of our mouth. And there's vibrations occurring inside the larynx, right? And it comes out, it's compressing and expanding the air as a wave. So there's a vibration occurring in the air, and that's transferring energy. And that energy is in the form of sound waves, right? So there's a, you know, a famous line from that movie in the 70s or 80s. I guess it was the 70s. I think it came out in 79, called Alien. And the you know, it's about a space alien that kills these miners that are in a spaceship. And the line is, you know, no, in space, no one can hear you scream. And that's true. There are, you know, when you watch a movie of something exploding in space, there is no sound wave because there's no air, right? So you have to have something to expand and compress for a wave to propagate. So waves have certain, you know, rules of propagation, of moving. And so if you don't have air or something else, sound waves will not transmit, right? Now, sound waves can transmit through solid material as well. So if you have an earthquake, the waves will propagate through the land, and they actually propagate faster generally through solids than they do through gases. There you go. Okay, sorry here. Just need to turn this off. There we go. Otherwise, people will be communicating. Okay. All right. So we're going to talk about light. So light is a form of electromagnetic wave. Now that's a mouthful, so we often abbreviate it as, just like with kinetic molecular theory, we call that CAM theory, we often abbreviate this EM wave, EM for electromagnetic, which suggests that it has something to do with electricity, right? And it has something to do with magnetism, electromagnetic, right? So in fact, it does. Light has a component that is electric and a component that is magnetic. And that's an interesting aspect of it that we won't really go into in too much detail in this course. That's really something you would cover in a second semester of physics. Okay. So, so essentially, what we think of as light is something that's a wave. So it's common to represent waves using what are called sine waves, right? So this is something that's oscillating. So it's going up and down repeatedly. And so I'm going to put a coordinate system in here. This is our x coordinate, and this is our y coordinate, right? Cartesian coordinate system. There we go. And this is our wave. So the wave is something that is oscillating. It's going up and down, up and down, up and down. Now you can see ripples on the surface of water, right? If you drop something into a flat surface of water, the water is still. If you drop it, when it hits, energy is transferred from that object that you're dropping, transferred into the water, and the water will transmit that energy, generally not in the form of heat as much as waves. It's a very efficient way to transmit energy. So you'll see these ripples that go further and further and further and further out. And then at the surface of the water is going up and down, up and down, up and down, right? That's the wave, that's the oscillations of the water that's taking place. Sound waves do something similar with sound. And it turns out electromagnetic waves do too. They have this oscillatory or this vibrational component. They vibrate up and down, up and down, up and down. So the y-axis is typically called the height, and the maximum of that height is called the amplitude. So this would be called the amplitude. Okay. Symbol for amplitude is A. We generally don't worry too much about the amplitude in this course, but that is essentially a measure of how strong that wave is, right? Like how strong it is. The higher the amplitude, the stronger it is in some sense. Okay. Now on the x-axis, this could be different things. It could be positional. It could be space. So like, you know, what is the wave here? What is it there? What is it there? What is it there? Or it could be time. Sometimes we graph it based on time because this wave is changing over time. So sometimes this x is position, or it could be t for time. And it just depends on the context of what we're looking at. So our first calculation that we're going to do, we're going to look at this relationship. Okay. So it might be useful to think of these electromagnetic waves as in the following way. They're moving through space, okay? So, you know, think about it. The sun is emitting light. That light is flying. Now, notice the light is actually flying through space and there's no air, right? So electromagnetic waves are in some way different from many of the other different types of waves that you're familiar with, sound waves or well, sound waves, I guess, is the most common one, or water waves, right? Electromagnetic waves are actually able to propagate through space itself. And, you know, that gets into some deep stuff, but it's moving through time, but also moving through space. Okay. And so for that reason, we want to have a discussion about space. So this would be position, and I'm going to put X there. X, X is typically position. And then there's our Y there. And then here's our wave. It is useful to define a couple of what we call parameters, things that you would measure in terms of these waves. Okay. Notice the wave can be positive or it can be negative. That is a possibility, but we're not going to talk about that aspect of them right now. So the first parameter, the first measure that we're interested in is called the wavelength. And we're going to define the wavelength as the distance or displacement between two adjacent peaks. So how far are those peaks away from each other, right? Those are called peaks. You got peaks and troughs. The trough is the minimum, the peak is the maximum, right? And that is called the wavelength. And if you think about it, since we're measuring length or position on the x-axis, really what you're saying is how far apart are these peaks? The symbol we're going to call that is a lambda. So if you know the Greek alphabet, you're at an advantage here. We use the Greek alphabet quite a bit when we start doing topics like this. So this is pronounced lambda. It's just the lowercase l, essentially, for the Greek language, okay, lambda. So if someone says lambda is, what they're talking about is the wavelength, okay? And it's going to have, so the wavelength is going to have length units. So typically those are meters, centimeters, millimeters, nanometers, but all these prefixes with meters, right? So those are the units of wavelength. The old days we might use inches or meter or yards or feet or some, but we're going to use, sorry, there's an H at the end. We're going to use meters. Okay. Now, it's also important to note that there's a time component to these waves as well. Again, the amplitude is this peak, the height. That's your amplitude right there. We can also plot it in time because it's moving through space. And so, when you think about light, what's happening, right? So you have a light bulb, the light is being transmitted through space, whether there's air there or not, transmitted through space, hits your eyeball. And then there are molecules in your eyes that are capable of absorbing the energy of those waves and eventually sending a chemical signal to your brain that is then perceived based on your experiences and your genetics, perceived as something, an object, right? So we have time, sorry, I didn't write that very well, time on the x-axis, so it's happening through time. And again, this is just y. And so it's going to be plotted the same way, right? It's the same way, we're just plotting it versus time. And what you see is that the wave is actually changing in time. The wave has a larger amplitude and then, well, it has a larger height and then a smaller height. It sometimes goes negative, but it's occurring. And so the distance, it's not length, it's time, right? So the amount of time between two peaks is called the period of the wave. And we actually don't use the period in our calculations. If you take a physics course, you'll calculate the period of a wave. But we generally aren't concerned with the period. We're more concerned with the vibrational nature of light, that it's undergoing some sort of vibration. So it's not unuseful. It can be useful to think of light as these waves that are vibrating in and out, and they vibrate with a certain period. How long does it take for the vibration to take place? So a long period would be slow vibration. That's a long period. If they're vibrating very rapidly, that's a short period. But there's another way of thinking about that vibration, and that is to use the reciprocal of the period, 1 divided by the period. If you take the reciprocal of the period, what you're measuring is how many vibrations occur in a given amount of time. So if something has a long period, so it's really slow vibration, okay? So that's a long period. It's taking a long time for that to happen. The number of vibrations that are occurring in a given amount of time is very low, right? It's a very slow vibration. We call that measure of the vibrations the frequency. So we have this thing called the frequency. And I'm going to use the symbol F for frequency. And it is equal to 1 divided by the period, or 1 over t. Okay, you don't really need to worry about the period in this course. It's the frequency we're going to be concerned with. So the frequency of this wave. So here's the idea. If something is vibrating very rapidly, that's a high frequency. If something is vibrating very slowly, that's a low frequency. So we can have high and low frequencies. Okay. Now, as I said, these waves are vibrating. They're moving through space. So they have a speed, right? If something is moving through space, it's moving at some speed, right? So they're moving through space, these waves, they're vibrating, and they have a sort of size, a length. So what we do is we put it all together and we define the wavelength times the frequency, and that is equal to the speed of the wave. So this is true for any wave. Any wave that has, a length and a frequency has a speed. It's moving, right? So we're talking about moving. We're talking about what are called traveling waves, waves that are moving through space. So I'm going to put in the symbol here. The wavelength is lambda. I'm going to put a little dot instead of an X. And then I'm going to put the F in there for frequency. And the symbol we're going to use for speed, when we're talking about the speed of a wave, we use a very specific symbol. It's a C, a lowercase c, like specific heat capacity, right? So you can see that sometimes we get confused with our units. With our symbols. And part of that just has to do with the fact that there's only 26 letters in the alphabet. If we had an alphabet of 150 letters, we'd be much better off for symbols, but we only have 26. Some languages might have even up to 32, but even that's not enough, okay? So there we go. In fact, we're using a Greek letter, a Greek symbol for one of these, right? So for waves, this is the symbol we use for speed. So this is wave speed. Okay. And it's a very simple relationship. The wavelength times the frequency is equal to speed. Now, just to kind of show you, because period is 1 over frequency, these are the reciprocals of each other, we can think of speed as being distance over time, right? The distance traveled over the time it took to travel that distance. So distance is wavelength, and then period is time. So it's really lambda over t, but since frequency is 1 over lambda, okay, what you get is lambda times f, right? So your speed would be lambda times f because f is 1 over t, and that's why that equation looks like it does. Okay. So there you go. So that's very useful. So what we're going to do initially is we're going to just do some simple calculations of wavelength and frequency, get used to the units. What units would we expect? Well, just to remind you, this is a distance, so it's going to be length units. And this is frequency. Well, what's frequency? Well, it's 1 over the period. So period is time units. So this would be 1 over time units, right? That would be 1 over time. So that's often, 1 over time units is usually like 1/seconds, right? 1 time units. That's a little awkward to have units that are 1 divided by time. So usually it's written this way, not always, but usually written this way. Seconds to the -1. Seconds to the -1 means 1 divided by seconds. Okay, and that's what we would expect because it would be 1 time units. Now we can also think of it this way, just for your own conceptual understanding. It's vibrating. The waves are vibrating. So the question is, what's the frequency? Well, the frequency is essentially how rapidly they're vibrating. So you can think of it as how many complete vibrations occur in 1 second. So if I said the frequency was 10 reciprocal seconds, right? 1/seconds. That means it's going through 10 cycles every second. So higher frequency is faster vibrations. Lower frequency is slower vibrations. And then the wavelength is the size of the wave. And then the speed is how fast it's moving. Okay. So, and then the speed, let's talk about the speed. So it turns out that electromagnetic waves so EM waves, right? In a vacuum, they travel at a constant speed, which we call the speed of light. And the value is 2.9979 approximately. It's actually measured out to like 9 significant digits, but I'm just putting the first 5 times 10 to the 8th meters per second. Okay. That's called the speed of light. Doesn't matter what direction the light is moving, your perspective on the light. Doesn't matter if you're moving. From your perspective, it will still appear to move at that particular speed. It's a very large number, at least from our perspective. This corresponds to 186,000 miles per second, not per hour, per second divided by seconds. The circumference of the Earth at the equator is 25,000 miles. So that means that electromagnetic waves would, if you were to turn on a light bulb, at the surface of the Earth, if the waves could go all the way around the Earth, they would go around about 7.5 times every second. That's pretty fast, right? So that's why electromagnetic waves are so useful for communications. They travel so quickly, at least over those kinds of distances. The moon is about 238,000 miles from the Earth on average. So that's a little more, that's more than 186,000. So that means that light takes more than a second to travel to the moon, and then more than a second to come back. So there are experiments that scientists perform pretty regularly where they will shine a laser, a high-powered laser from the Earth to a reflecting mirror that's on the surface of the moon, and then it bounces off the mirror, comes back to the Earth, and they make measurements of how long it took. Since you know the speed of light and you know how long it took, the time, you can calculate the distance, and that's done on a regular basis. Okay. Okay, so there we go. So that's the value we would use. Now you might say, well, wait a minute, what do you mean by in a vacuum? We're not in a vacuum, we're in air. And that's true, but it turns out air is pretty diffuse. There's not much matter in air. Like if you take like a little ball of air, there's very few molecules in there relative to solids or liquids, right? So it turns out the difference in speed is very small. Now, there is a difference, but for our calculations, it's not going to show up, so we don't need to worry about it. So we can use that value in air or in a vacuum. Now, light does travel quite a bit slower through solids and liquids because those materials are much more dense, 1,000 times more dense. So in fact, light does slow down as it travels through solids or liquids. So, when the light hits the surface of this glass and the water, it's going to slow down. Okay. But we're not looking at those kinds of problems. Again, when you take physics and you're doing optics, you'll talk about this thing called the Index of Refraction, which is related to how fast light is traveling through these materials. Okay. So we can use this value here. Sometimes people just round it off. They round it off to 3.00 times 10 to the 8th meters per second. Some people round it to 3.0 times 10 to the 8th meters per second. I go back and forth. Sometimes I use 3.0, or if I'm doing an estimate, I'll just use 3 times 10 to the 8th because it's pretty close to 2.9979. It's only off a little bit. Okay. So the first kind of set of equation, or first set of problems you're going to do, I know this is a lot of background, is to just start calculating wavelength and frequency based on this formula, based on this equation. Okay. Now, I'm going to do the first problem just so that we can kind of get started here. And then I'm going to come back and talk about the electromagnetic spectrum as well. I want to get into that today so that you have a little bit of background in that one. Okay, so let's take a look at this first one. Interconverting the wavelength and frequency of electromagnetic radiation. Suppose a popular FM radio station broadcasts radio waves with a frequency of 94 megahertz. So that's pronounced 94 mega. Mega is a prefix, right? Megahertz. The Hz stands for hertz. So that's a measure of frequency, megahertz. We'll talk about the units in a moment. Calculate the wavelength of these radio waves and round your answer to 2 significant digits. Okay, so 94 megahertz FM. So notice this is not visible light. It's FM radio station. That's not visible light. You can't see radio waves. Our eyes can't see radio waves. It'd be kind of crazy if we could. So I'm going to talk about the electromagnetic spectrum, but radio waves are also a form of electromagnetic waves, just as visible light is, Roy G. Biv. Okay. So what about this 94 megahertz? That's a frequency, but I haven't talked about hertz. So let me talk real briefly as we go through this problem. Okay. So our frequency is 94 megahertz. Okay. Yeah, 90. Well, in the United States, FM radio is done odd numbers, 94.1, 94.3, 94.5, so that they don't interfere with each other. So they always end in a point with an odd number. Some other countries, I think, you actually use even numbers, 94.2, 94.4, for example. FM radio goes from around commercial FM radio goes from 88 megahertz to 108 megahertz. So this is in that range right there. Okay. Now, what's this Hz for hertz? A hertz is abbreviated as Hz, and it is equal to 1 over a second. It's the exact unit that we were talking about earlier, reciprocal seconds, right? Reciprocal seconds, seconds to the -1. Same thing. It's just a name for it, just like we did with pressure units. The Newton per meter squared was called a Pascal. The kilogram meter per second squared was called a Newton. The joule was called a kilogram meter squared per second squared. We're just giving a name to it. So 1 over seconds, or reciprocal seconds, is a hertz. So no big deal. So that means it might be useful when you do the calculation for dimensional analysis purposes to call this 94. Now, what's mega? 10 to the 6. Mega's big. So times 10 to the 6. That's 94 mega. And then 1 over seconds. So I like to write it this way, 1 over seconds, if I'm doing a calculation. If I just wanted to write it, like to make it look nice and clean, I would just write s to the -1. But if I'm doing a calculation, I'll put it in the formal 1/seconds, just for dimensional analysis reasons. Okay, so they're asking us for the wavelength. Very simple. We have our relationship lambda times f equals c. So if we want to have wavelength, we're just going to divide both sides by frequency. Right? Divide both sides by f and you get your wavelength. So again, the speed of light is a constant, 2.9979 times 10 to the 8th meters per second, divided by our frequency, which is 94 times 10 to the 6th, that's mega, 1/seconds. And so by writing it as 1/seconds, you can see the seconds are both in the denominator, so they cancel. So we don't really have any units in the denominator anymore, it's just a 1. But we do have units up here in the numerator, that's a meter. So our answer is going to be in meters, which is perfectly fine. Then you just go through the arithmetic. So really you got, I don't know, it's going to be in the, like a meter, isn't it close to a meter, like maybe 2 meters or 3 meters or something like that. So let's see, 2.9979 times 10 to the 8th over 94 times 10 to the 6th. Yeah, 3 meters. So I'm going to round it to 2 sig figs, so 3.2 meters. Okay. So what does that mean? What that means is FM radio, these waves are transmitted through space, through, air, and they can go into space, right? If you're communicating with astronauts in space, it's going to go through space as well. These waves are vibrating, and they're vibrating at a frequency of 94 times 10 to the 6, 94 million, right? Mega is a million. So 94 million times every second. I can't move my fingers that fast. The wavelength, the size of the waves, so as they transmit, so imagine you got this antenna, right? And it's transmitting these waves. If you actually study one of those waves and you look at the wave, the wavelength is 3.2 meters. That's pretty big, right? That's like over 9 feet. It's, a small room might have a width of 9 feet or so. So that's like 9.3 feet or something like that. So 9 feet, 4 inches or something like that. Yeah, I've seen bedrooms that are that small. So that's essentially how big the wave is. And this actually can create issues for tunnels. So if you don't build transmitters in the tunnels or repeaters in the tunnels, if you're driving a car through a tunnel, 3 meters is about 9 feet. So that's, that's like about the size of the wave, right? So like, well, let me draw it this way. Sorry. Oops. Right. So like the wave, if you're trying to get that wave through the tunnel, it could be kind of a problem because the height of the tunnel is about 9 feet, maybe 10 feet or 11 feet. So that wave just kind of barely fits in there. So FM waves, they kind of barely work through car tunnels. They kind of do. But AM radio, what happens with AM radio is that the waves are even longer. AM radios, the waves are 100 times larger. 100 times. So 100 times 3 is 300 meters. So AM radio waves, they're not really big enough to actually fit into the tunnel, so they don't transmit very well. So if you're listening to an AM radio station and you go into a tunnel, you may not hear that station anymore because the waves are just too big to fit in there. Okay, so there's our first calculation. All right, let's see if there's any that are different. Okay, let's look at another one here. There we go. X-rays have a wavelength. So X-rays, right? So X-rays are also electromagnetic waves. They have a wavelength. that is small enough to image individual atoms. Pretty amazing stuff. But are challenging to detect because of their typical frequency. Suppose an X-ray camera uses X-rays with a wavelength of 5.53 nanometers. So now we're given the wavelength. Calculate the frequency of these X-rays. So X-ray frequencies, it's a little tricky. I'll go through a little bit through the units here, but anyways, we're using a wavelength. So we're given the wavelength here, right? That's what's given, 5.53 nanometers, and we're asked to find the frequency. So the opposite of what we just did. So 5.53, oops. 5.53 nanometers. So the wavelength is 5.53 nanometers, and we're asked for the frequency. Okay. Again, the speed of light is a constant, so we have that one. Okay, and there's your speed, right? Okay, well, pretty simple. But what I'm going to do is I'm going to write this in meters. So nano, you're going to use that a lot in this chapter. Nano is 10 to the negative 9. Micros minus 6. Nano is minus 9. So 5.53 nano, 10 to the minus 9 meters. Okay, now we calculate the frequency. So lambda times f equals c. So we want the frequency. So f is equal to c over lambda. So that would be 2.9979 times 10 to the 8th meters per second over 5.53 times 10 to the negative 9 meters. Meters cancel, and you get 1 over seconds, and that's perfectly fine because remember, 1 over seconds is seconds to the minus 1, which is equal to hertz. Okay. So let's see, it's going to be a really big number. Ignoring the decimal values, the 2.9979 and the 5.53, if you take 10 to the 8th, very large number, divide that by 10 to the minus 9, very small number. A large number divided by a small number is an even larger number. You're going to get a huge value out of this. So 2.9979 times 10 to the 8th over 5.53 times 10 to the minus 9, you're going to get 5.42 times 10 to the 16. Okay, so typically we might say the frequency is 5.42 times 10 to the 16 hertz, but we might decide to use a prefix because that value is so large. So 10 to the 3 is kilohertz. 10 to the 6 is megahertz. 10 to the 9 is gigahertz, right? 10 to the 9 is giga. 10 to the 12 is terahertz. Okay, so you'll see often, you know, going up to these values, you know, the next one I think is exa, 10 to the 15th. Sorry. That's less common that you're going to see that. Terahertz is usually where people will end up, but there's exahertz as well. So there's 10 to the 15 is 1 exahertz. Okay. So what you could do is you could do terahertz because 10 to the 12th, we're getting close to that. So what you would do is you'd say, if I move the decimal point 4 places, now you get 10 to the 12. Right? If you move it 4 places, you get 10 to the 12. 16 minus 12 is 4. So now you've got 54,200. So this could be 54,200. And now you could put in your terahertz. So that would be 54,000 terahertz. Or you might say, well, no, let's go up to the 15 exahertz, right? So then now you only got to move it one place to make it 15. So 54.2 exahertz. Right. So sometimes the answers when people do these calculations, just like FM radio is megahertz, AM radio is kilohertz, cellular communications are gigahertz, right? The newest technologies might become terahertz. So if we can develop terahertz technologies, we'll be able to transmit enormous amounts of information, okay? So sometimes just be aware you may see those prefixes pop in there, okay? Let's see. The next issue, I'm gonna do the electromagnetic spectrum. Okay, so I'm gonna have to bring up an EM spectrum for you. So that we can kind of talk about these. Here we go. Oh, this is from Wikipedia. Perfectly fine. Wikipedia is good. Let me just make this a little bit bigger. There we go. Okay, that shows up pretty well, right? Let me see if I can make it a little bit bigger. There we go. Okay, so as we saw from the previous examples, there are different types of electromagnetic waves. There's visible light, Roy G. Biv, but there are also other forms like FM radio waves, X-rays. And so this little picture here shows you the 7 categories of electromagnetic waves. For a while, it was suggested there might be 8, but it looks like it's 7. So the first are the radio waves, and these ones have the largest wavelengths, the longest wavelengths. So when we talk about wavelength, we use the term long for big and short for small. So short wavelength, long wavelength. Okay. So radio waves, that's AM radio, FM radio, even kind of getting into the cell phones, I guess 2G, about 3G or 4G. At least early cell phone communications were in the radio wave. Now they're close to they're kind of into the microwaves now. In any case, this picture here is just kind of giving you kind of an image of size, right? So these are these gigantic buildings that exist around the world. This one, I forget what this one's called. It's a huge building in Asia, which are like 1,000 feet, right? So the point is that the size of these waves are huge. They're very long wavelength, okay? So they're kind of representing that here. Look how slowly that's changing. That's a very long wavelength. It's very gradual, okay? Does it penetrate the Earth's atmosphere? Yes, radio waves can be used to transmit through the atmosphere, okay? But what about their frequency? Well, mathematically, think about it. Since lambda times f equals a constant, if one of them goes up, the other one has to go down. It's kind of like that old, that boils law, PV equals a constant. If pressure is higher, volume's got to be smaller, greater. I mean, if pressure is greater, volume's got to be lesser. So same thing here. If the frequency is high, the wavelength's got to be short. If the frequency is low, the wavelength's got to be long. So the long wavelength radio waves have very low frequencies. So the terminology we use for frequency is low high. So low frequency, high frequency. So there you go. And then it turns out that we're not going to really go into this. This is something you would take in a physics course or a more advanced chemistry. It turns out that everything emits electromagnetic radiation, electromagnetic waves. Everything does. And it depends to a large extent on the temperature. The colder something is, the lower the frequency of the waves that are produced. And this is the basis of those night vision goggles. Essentially, what happens is a human body, it has a pretty high temperature relative to things around it, not the sun, but space. And so we actually emit infrared radiation. And so the night vision goggles, what they're able to do is to detect, to absorb infrared radiation. And so because we are warm-blooded, we're producing electromagnetic waves in the IR region. Okay, so low temperature, in fact, they're showing you, look at these low temperatures. So radio waves correspond to really low temperatures. This is 1 Kelvin up here, right? So there you go. Okay. So buildings, that they're big, long wavelengths. Then you get to microwave. Microwaves are shorter wavelengths, right? The wavelength's smaller now, 0.01 meters approximately, right? And how big is that? Well, that's like the size of an animal, like a butterfly or something like that, right? So humans are a little bit bigger. Butterflies are, you know, a little bit, well, actually 0.01 meters is a centimeter, so that's about that big. So not even a butterfly, like a large ant or a bee or something like that is 0.01. But that 0.01 is right here. So, you know, there's kind of giving you a gauge there. So the frequency is getting larger. Look what happened to the frequency. We went from 10,000 to 100 million. 100 million, right? Okay. Now, temperature is still very cold. Go up to infrared, right? So now infrared, the wave is getting shorter. So now it's pretty small. It's like the little hole in a needle. That's really small. And the frequencies are much higher though, 10 to the 12th. Now we're up to trillions of vibrations every second. And now you're starting to get up to some higher temperatures. It's still pretty cold, liquid nitrogen temperatures, but so liquid nitrogen is producing those waves and radiating them out. Okay. Now you get to even shorter wavelengths. Now we're starting to get into visible light. Now, what are we able to do with visible light? We're able, using microscopes, to focus visible light to see cells and even organelles within cells, right? Mitochondria, nuclei, if they're stained anyways. So if that's the case, really what we're saying is that the wavelength of this light is now getting short enough that it's able to resolve these fine structures within cells, okay? So there you go. So there's your shorter wavelength, frequencies getting larger, right? So visible light has frequencies in the terahertz range, hundreds of terahertz actually. And then now look at the temperature. If something is glowing visible light, what do we know about it? Think of the sun, right? The sun's hot. It glows with yellow light, with white light, actually. If you have an electric heater and it turns red hot, it's really, really hot. Well, it's corresponding to thousands of degrees, right? So that's why we don't glow in the red, because we're not hot enough to glow in the red. If we did, we would die, right? So things that are really, really hot start to glow. So, you know, like light bulbs, right? They're really hot, so they glow with visible light. Very high frequencies. Then you get the ultraviolet light, ultraviolet, UV, right? UV, really short wavelength, 10 to the -8. Now you're starting to get to the size of a molecule. So if you want to resolve the size of a molecule using light, you kind of have to start moving into the ultraviolet. That doesn't work very well because we don't have very good glasses that can transmit ultraviolet. But there's a Taiwanese company that has these things where they can, these machines that can use extreme ultraviolet light, which is almost X-rays, to do lithography and make these chips that we all depend on. Okay. Actually, it's not Taiwan, it's the Netherlands. Okay. So very high frequency. So ultraviolet waves, very high frequency, 10 to the 16 hertz, 10 to the 17th hertz, huge temperatures. So stars that are even hotter than our sun are going to start emitting a lot of ultraviolet radiation. Then you get to these things we just did a problem on, X-rays. X-rays are now have a wavelength that are the size of an atom. So that, when they said resolving, being able to look at images of atoms and stuff like that, it's not that easy. And the images aren't that great, but it is possible to do some imaging then of atoms in certain circumstances. Now you're talking about really, really short wavelength, 10 to the minus 10 meters. And the frequencies are enormous, 10 to the 18th hertz. And the temperatures that correspond, something that would actually emit electromagnetic waves that way, it's going to be really super high temperature. Okay. Last one, gamma rays. Gamma rays are the shortest wavelength of all of them, 10 to the minus 12, 10 to the minus 13 meters. Those correspond to huge frequencies, 10 to the 20th. Gamma rays are produced in a couple of different ways. One is through the nuclear, where a nucleus of an atom breaks apart. And so you see that in radioactivity of like uranium and stuff like that. So that can happen. That's one way that they're produced. The energies of a nucleus are enormous. And so when the atoms break apart in the nucleus, you can get these gamma rays that are produced. The other ways is through stars. You just have to have these massive stars that explode, and they do these things which are called gamma ray bursts. They produce these enormous energy, right? So very high frequency and corresponding to just ridiculous temperatures that are not within our experience. Okay. So there you go. So that's called the electromagnetic spectrum. There should be a mnemonic. I never really thought about that. I bet you there's a mnemonic for this order. But you can do it in terms of frequency or wavelength and then just reverse it for the other. So radio, longest, radio waves are big. So there's radio waves, microwaves, infrared, IR, then visible, then UV, and then X-ray, and then gamma, going all the way to shorter and shorter wavelength. And then frequency would just be the opposite. Okay. So let's take a look at an ALEKS problem. It says, understanding the organization of the electromagnetic spectrum. A few different types of EM radiation are listed in the table below. So complete the table by ordering these types of radiation by increasing frequency, wavelength, and energy per photon. I haven't talked about energy. Energy actually comes into the next topic, but I'll just mention it briefly. Well, temperature is related to energy, right? So you could kind of use that as your logic. So select one in the second column for the type of radiation with the lowest frequency, okay? So lowest frequency, 2 would be the next highest frequency. And then, so we'll do frequency and then we'll do wavelength and we'll do energy, okay? So 1 is the lowest frequency, okay? So it looks like it's microwaves, blue light, UV, and X-rays. So microwaves, I'm going to actually use the symbol micro. So microwaves, blue light, that's visible, right? UV, and then X-rays. And then we're going to do the order of frequency. F for frequency, we'll do that first, okay? So 1 is the lowest frequency is the way they want it. So, it's pretty simple. You just look at your little diagram, but think about it. The lowest frequency are the ones with the longest wavelengths, but the lowest frequency are the ones that are vibrating very slowly. And that would be radio waves would be the lowest, and then it's microwaves, and then it's infrared, and then it's visible, and then it's ultraviolet, and then it's X-rays, and then it's gamma rays. So the lowest one looks like we don't have any radio waves, so it just would be microwaves. So that would be 1. The next one up is visible light after, well, then it goes infrared. but there is no infrared in this particular problem, so it's not there. Next one is visible. Blue is visible, so that would be 2. And then ultraviolet comes after visible, so that would be 3. And then the highest frequency, the one with the largest frequency, would be the X-rays. Okay. Okay, so let me just go back to the instructions here. So we're going to do the same thing with wavelengths, so order of wavelengths. But now the order is the opposite, right? The higher the frequency, the lower the wavelength, or the shorter the wavelength. So we're going to go the opposite. So the X-rays have actually the shortest wavelength. Okay, so 4 becomes 1. And then, 1 becomes 4. The microwaves are the ones that have the lowest frequency. They're going to have the largest wavelength, the longest wavelength. So that's going to be a 4. And then these will just get flipped too, right? So there you go. And then energy. Now, I haven't really talked to you about energy because that really kind of comes into when we talk about photons, which is the next section. But let me just say this. Let's think about it. We won't get into photons and energy. Let's think about temperature, right? So what we said was, as the temperature increases, okay, the frequency was increasing. That was the pattern in that graph. So remember, temperature is a measure of energy, right? The average kinetic energy. So in a sense, these these electromagnetic waves are they have energy. And so we'll talk about that in the next section. But so you can kind of think of it in terms of temperature. The way it went was the higher the frequency was, the higher the temperature was. Remember, the gamma rays were all the way at the right, and they had enormous temperatures, whereas the radio waves were so low in terms of temperature that they were like below 1 Kelvin, okay? So the temperature or energy, okay, temperature is a measure of energy, are directly proportional or directly related to the frequency. And they're not directly proportional. Take that back. They're directly related. So as the temperature goes up, the frequency goes up and vice versa. So that means we're going to use essentially the same order that we had here. 1, 2, 3. Oh, did it really go in that order? It really did. It really did go 1, 2, 3, 4 for frequency and for energy. Okay. So what I'm doing is I'm saying temperature and energy are related, right? Average kinetic energy, 3/2 RT, right? Energy, temperature. Okay. So there you go. So that's section 6.1. A lot of background on that, right? So this chapter has a lot of ideas, a lot of concepts that may or may not be familiar with you. So we're going to go a little bit slower with this one because we have a lot of new ideas that are coming into here. We have to do some physics in this chapter. So I may only get through like 1 section a day on this. All right. So have a great day and good luck with all of this. And
ask a random question.
Is it related, or is it, how random is it?
No, it is related.
Oh, it's related. Okay, go ahead.
Do you want to stop the recording? I don't know.
Sure.